All right, fantastic. I think we are just about ready here to get started. So thank you everyone today for joining us here for the Monsoon seminar series. Today we are joined by Nicolas Waldmann from the University of Haifa. And so Nicolas Waldmann is a geologist and a sedimentologist with a wide experience across marine and lacustrine expeditions. I think you've also been involved with a variety of IODP and ICDP drilling programs as well, which I'll detail a little bit below. And so Professor Waldmann, he received his Master's of Science from the Hebrew University in Jerusalem and his PhD from the University of Geneva in Switzerland. And then following his 2-year postdoc at the University of Bergen in Norway, in which he basically dealt and researched gas hydrates across the North Atlantic, he then returned to Israel and he founded the Basin Analysis and Petrophysical Laboratory, or PetroLab, at the University of Haifa. So currently he hosts a lab of 15 team members. That's pretty big, including a variety of research personnel, postdocs, PhDs, and master's students. And his research projects are across a wide range of disciplines and are multidisciplinary, of course, and they include paleoclimate reconstruction across sub-Saharan Africa using lake records, and even studying the causes for mammoth extinction across the Bering Strait using biomarkers. And as I mentioned earlier, he's participated in a variety of marine and lake research expeditions, including the IODP leg in the Maldives, offshore of Svalbard, and of course the ICDP projects in Lake Chala, the Dead Sea, and the Lake Namso project. And even Lake Chad. Cool. And then in 2013, Professor Waldmann was awarded the Krill Prize for Scientific Excellence from the Wolf Foundation. And so without further ado, I'll let the speaker tell you a little bit about monsoons in the Near East for the rest of today. Thank you.
Thank you very much, Tara, and thank you very much for the introduction. So indeed, I am going to talk about some evidence of northward migrations of monsoon fronts during the Pliocene and early Pleistocene in the Near East. So thank you everybody for being there virtually. Okay, here we go. So I actually want to start by why the Pliocene. So first of all, what we are experiencing since the LGM during the Holocene is a wide increase in temperatures, which present present models show an increase toward the future due to global warming and anthropogenic influence. But when we are watching this curve in the more long extent, we see that basically we are getting into temperatures which were very typical for the Pliocene epoch. So we are basically breathing the air that was with the same kind of atmosphere that prevailed during the Pliocene, at least for a long period of time. We had those times of high temperature during previous interglacials, but as a long sequence, a long time frame, it is indeed the Pliocene, the best equivalent and analog. Aside of temperature, when we are also observing the reconstruction of CO2 in the atmosphere, we are definitely breathing. Currently, we are over 400 ppm of CO2 in the atmosphere, and reaching the same levels that the last time we were in the Pliocene. And not to mention that the different projections for the future, most of them point to levels of CO2 in the atmosphere that they are reaching far beyond the Pliocene and into the Mesozoic. So we are definitely getting into a period of time in which the Pliocene is the best analog for comparison. And actually, in order to understand the present trends in climate warming and to provide the best tools for modeling future trends, the Pliocene is one of the best epochs to study. So actually, the Pliocene has been included in the latest IPCC report in 2021, the physical science basis, and I highlight some of the phrases that they are written in the IPCC, such as the most recent interval with mean global temperature substantially warmer for a sustained period, around 2 to 3 degrees centigrade above pre-industrial temperatures, and also the most recent interval with atmospheric CO2 concentrations, as I mentioned before, and the most recent period which continents and ocean basins that had a similar geographic configuration as present. Basically, the world was very similar to the one that we are living today, not the world that the dinosaurs were prevailing. That's a different planet, different ocean configuration, different conditions. That the Pliocene is pretty much very similar to the one that we are living today, and the one that we are perhaps going to breathe in the near future. So what happened from the Pliocene into the Pleistocene? There are several issues that appear to have happened and caused the global cooling and the northern hemisphere glaciation overruling our planet during the Quaternary and later on. One of them is the Panama Seaway closure that started to occur 13 million years ago and promoted an increase in salinity contrast between the Pacific and Atlantic Oceans. Also collapse of permanent El Nino conditions with warmer temperatures in the eastern equatorial Pacific during the Pliocene, causing an increase in water vapor within greenhouse effects and reducing the area covered by highly reflective static cloud. And also increase in mountain belts uplifts such as the Rockies or the Alps and also the Himalaya, which change the atmospheric circulation patterns. And of course, also leading to carbon dioxide concentration in the atmosphere that were around 400 ppm per volume in the Pliocene, increasing level during forward into the early Pleistocene due to the global cooling conditions. So these are one of the some of the conditions that led into the cooling of during the Pleistocene. Basically, in order to understand exactly what were the conditions, we probably need some kind of a machine to go there. It would be excellent if we had one of those. Maybe the next generation will do invent, but until we get there, we have our sediments, of course, to go back into the future. Let's say is the best analog back into the future. This lesson. So when we check the ocean basins for Pliocene platform and foraminiferal record, some of them are highlighted in this map of the globe. We see that there are areas with lacking information, such as the South Pacific or the Arctic, of course, but also some of the major areas that are, of course, lacking is all the continents. We have information on the continents, but not as much and not as pristine or continuous as the marine environment, but also from the Mediterranean, as you can see. Not so much has been done over there. So when we go to the Mediterranean during the Pliocene, this is the way it looks like, very similar to what we have today. There is already some kind of form in Italy. All what you see here is records for Pliocene around the Mediterranean, in Europe and Northern Africa. We see in the Levant also some kind of a lagoon, which actually pretty much appears to be true. Not necessarily exactly in this configuration, but there was some kind of a lagoon over there in the East Mediterranean. But when we have a look in the East Mediterranean basin more in detail, this is the way it looks like today. And I'm going to give you basically several archives in this talk for how the area of the East, the Near East reacted during the Pliocene. From one side from the Mediterranean and 3 sides from the continent, from the Levantine corridor, okay, which is over there. So when we have a look in the East Mediterranean, the Levant Basin, we see here what is the morphology of the seafloor extracted by the 3D seismic data. In this case, it's geophysical prospectrum of the Saramira. Okay, and what you can see very nicely is the existence of several seafloor channels related to the Nile fan, some faulting related to the presence of some tectonics under the eastern part of this area. But when we have a cross section across this, exactly across the Mira-1 well, we can see the seismic profile going down until 2,100 meters. This is in depth, not in time. From west to east, you can see the seafloor down there with the present channel of the Nile related to the turbidity flows of the Nile, hypopycna flows down from the Nile fan. And you can see down into the depths with several of the units, which in this case are divided into major two. Seismic unit 1 below this very prominent reflecton, which is the top of the Mycenaean salinity crisis. Okay, the evaporates units, the salt and some gypsum. And above that, which I'm not getting through, this is the Miocene, and above that will be the Pliocene-Early Pleistocene, unit 2B, 1, 2, and unit 2B and 2C, basically. So what we can see, I'm not getting through too much the geophysics. It was published by one of my students in 2018. But what is very much interesting that there are some units in which we can see some distortions down there of morphologies, U-shaped morphology, and some units that you don't see them. So when we have a closer look, for instance, these 2B1 and 2, we can see that these units are, some of them they are U-shapes, and some of them are more confined and V-shaped. Okay, and we definitely define them into these two types. Type 2 it will be the U-shape, the yellow here marked, and type 1 will be the black here, more confined, more deep, more V-shaped. We did it in all the seismic profile, in all this cube, and it was a statistical work done by the student. And here I am just showing you one of the lines, of course. But when we have a look on this period of time, which is in Pliocene, and check also the gamma ray, which is obtained from the well, we can see very nicely how it varies from in the unit from high to low, and then high, and then low, and then high again, exactly during the same units in which we can see these U-shaped valleys and V-shaped channels, sorry, which basically are interpreted as a change between the sand to clay ratio, with an increase in sand material towards the top in this channel, and then towards the bottom is a decrease, and then again and again, like 2 cycles of increase, decrease of sand to clay amount in these units. So when we see that, actually the variability in the sand to clay ratio matches very well with the variability between type 1 and type 2 types of channels. And what we understand by that is, of course, a relation, very straight and direct relation with the sea level oscillations, going down and then high and then down again. Sorry, up, down and up. Okay, but also an influence of enhanced monsoonal activity in the eastern part of North Africa, Ethiopian islands, the highlands of Ethiopia, and the sources of the Nile River, which provide more with the material to the East Mediterranean during enhancement of the monsoons fronts, of the African monsoon fronts during this period, with providing more with sediments into the deep Levant. So in short, what we see here, although the time frame is a little bit problematic, we do see that the cyclicity falls around the top of Zanclean and beginning of Piacenzian in that time frame of the Pliocene, with a cyclicity that is probably related not only to seafloor, to sea level oscillations, but the monsoon's activity over Africa. Although again, I highlight the problematic of establishing correct chronology here, since we are basically dealing with a well bore. But when we go for other evidences of monsoons in the Levantine corridor, we go over there, and we are dealing with the Erech El Ahmar formation. This is a new project that recently I am leading in Haifa with my team. And the Erech El Ahmar formation is a lacustrine sequence, which is over 150 meter long, which is exposed south of the Sea of Galilee, something like 10 kilometers south of the Sea of Galilee. What you see here is the exposure, is a picture. Is a drawn picture of the exposure. You can see the sediments laying, tilting 15 to 20 degrees toward the east. This will be here the Jordan River, which delimits the border between Israel and Jordan. So all the landscape over there basically is Jordan, not Israel. And here this will be Israel. Here, this is our cards over there for scale. You can see over there. So basically, this formation was not too much studied in the past, but it was studied in 2001, a publication that Hagai Ronet and colleagues, they published paleomagnetism in order to constrain the formation. And later on, 10 years later, by Davis et al., with cosmogenic isotope studies done in the same sequence. And basically, with the combination of both, the constraint of the sequence is between 3 to 4.5 million years old. But the last word has not been said, and the present study also tried not only to try to understand the environment, but also to try to better constrain the chronology here. Previous studies in the formation, also in another outcrop, which is something like 3 kilometers to the side, have identified a very excellent preservation of fauna. In this case, a mammoth tusk. A mammoth tusk, which also is pointing to what different kind of environment and conditions of the Near East, much more different than the currently today. The only problem here is that this 7-meter outcrop was very well studied also by Ostrokots, by our colleagues, in this case the Mammalia by Rivka Rabinovich, the Ostrokot studied by Stephen Mischke, but in any case, the correlation between this side and the other side, the main side that I show you in the picture, is kind of problematic, and we need still need to connect between these two sides. So it's an island of information concerning the ages. So we don't have really good ages of this side. So what we tend to do in the new study is to reconstruct the environment, to understand better the environmental conditions in the Levant during the Pliocene, and to try to provide better ages for the formation. So what you see here is a new picture of the formation. You can see the very well layering between dark, white, whitish and more dark, and then the sequence above over there. And what you see here, there are many sampling, but these are related to what I'm going to say. These are the previous cosmogenic ages. And we have sampled all along over 200 samples of the outcrop. for also cosmogenic, but also mainly for geochemistry and sedimentology and biomarkers. But also we did a core. We did already 4 cores in this slide, but I'm presenting the ERK2, which is the projected site will be exactly over there, which matches those ages that were done previously in cosmogenic isotope and were published in 2011. So here are the I show you the core and the projected approximately depth of the age done in cosmogenic isotope. We identified 3 major units in this core, lithological unit 1, 2, 3, which are basically very well identified by the different lithologies. We can see here in the color is more blackish. Everything is very well laminated, layered. Here is more blackish, here is more brownish, and here will be more yellowish. Okay, 3 major units, in which also comes here what I'm saying. We can see very well the difference. Here we see more brown clay. Here we see more clay and silt down there with some units that probably may be also tectonic influence. We are still in a tectonic basin, which probably experience seismics. Some of the highlights about the biology, we can see lots of fish tooth, lots of ostrocods, and interestingly also some mammal bones. In this case, pica from the genus Cocodonta, which looks like that little cutie animal, which again doesn't exist currently in this area of the planet. And it's a European fauna which prevails in more wet and cooling conditions than currently in the Mediterranean. So also it's pointing to an interesting observation about what were the conditions in the region. When we have a look about the end member analysis of our grain size, again, we see a very matching observations with the identified lithology done by observation of the core. And major, we can see that the units point to, we can identify events of more thin, fine sediments, probably dust events that we are still working on the data. One of my students is working on the data to identify much better the events of winds into the region. When we also check the geochemistry, we have a very good matching of the geochemistry with the identified units. We can see, for instance, here we see the magnetic susceptibility data and the aluminum, for instance, and potassium, and we see very well units such as the one with the pica remains, and identifying very well that unit in the different markers, the geochemical markers in the that they were measured, and the also the different trends in variabilities of the elemental concentrations varying accordingly to the different units. When we have when we do some statistical analysis of the different elements, what we initially identified is 3 major processes, and one which will be the autochthonous material, which is related to the calcium, sulfur, or fluorine in identified in the sediments, but also major 2 major sources. One will be the aeolian, as much as we interpret the potassium as an aeolian, but also a bunch of elements that they are probably related to fluid precipitation statistical according to the different units. So we're still working on the data and adding also this is done by our colleague Isla Castañeda in the University of Massachusetts in the United States. And what we see here is the biomarkers, the inalkane average chain lengths, and very few data. We are increasing the measurements, of course, and also the alkane concentrations here and the GDGT concentration. We see a very sharp difference between the upper part and the lower part, okay, which our interpretation is pointing to change between an old lake with an increase in alkalinity in C4 plants, probably pointing to warmer conditions, into an increase in C3 plants, probably pointing to colder conditions. What is very interestingly here to point is that, of course, we still need to do the isotope geochemistry, and it's going to be done in the current year. But it's very interesting to point that we are basically showing here different conditions than the one that prevails currently in the Mediterranean, because here we infer that we have high lake level conditions during warmer stage, and here low level conditions during a colder stage, which is opposite to what we see currently, for instance, in the Dead Sea. So we probably are showing here that even that we were warm in this part of the planet during this initial phase of the lake, we are still having a lot of precipitation and rain, probably not necessarily coming from the East Mediterranean, which is the current source of at least for the Pleistocene, for the lakes developing in the Dead Sea Basin, such as the Dead Sea. So we are in a condition which is probably pointing to different sources of rain. If we go to another site, which is also not so far from Eret El Ahmar, this is the Ubedia site. This is a new site that we are starting to explore as well. This is already in the Pleistocene. We are moving forward to the Pleistocene. We are in an already cool planet, and the Ubedia site has been the first site, basically is world famous because it has been the first site outside Africa with evidence for hominids, the Homo erectus. Since then, it was discovered in the 60s, 70s, early 60s. And since then, of course, there are more sites like Atapuerca in Georgia, in Flores Island in Indonesia. There are more sites, but this was the first discovered outside Africa, and has been widely studied because of that. You can see here the cross section of the formation, which has been done by Pickard and Biden in '66. You can see that it is an anticline or some kind of a sort of anticline with a fault in between. So it's a pretty complex site, and this has been due to post-depositional tectonic forcing, of course. And the formation has been estimated to date 1.5 million years old by different constraints, which I'm not going to get through. And we are trying again a new exploration that was basically the site has been open again last year. And we are trying to solve the age with colleagues from the University of Tulsa and the Israel Antiquity Authority, that they are leading the project. So in general, what we see here, the first general, let's say, stratigraphy, we see 4 different units: lower limnic, lower fluvial, upper limnic, upper fluvial. In my point of view as a geologist, what I see is an orbital cycle, maybe a low, high lake level. This is one of the points that we want to try to solve as well. This is the opening of last year or a year and a half ago, in which we opened again the trench that was opened in the 60s and detailed studies of the outcrop. In my case, what I came and what we can see here is the beautiful fantastic layers that they were resampled in much high resolution than was done before. And in my case, what I came to this project is providing the facility for drilling and obtaining a core. And this is what we did nearby the outcrop. And we succeeded to have a 97% of recovery with a geoprop push core and obtain a 70-meter long core. The core sections were brought to Haifa and were submitted to an MSCL multi-statistical logger for analytic measurements, including a magnetic susceptibility and gamma density. We didn't do per wave. There was no need here in this case, but also we sampled for grain size, geochemical measurements, and total organic carbon, the typical sedimentological measurements that we do after opening the core. The good thing here is that the core provides a very good and unweathered record of the sediments, which basically provides the means to further do biomarkers analysis, which are kind of tricky when we are doing them in an outcrop. So here again, the location of the core in relation to the outcrop is somewhere around there. So we estimate that we went through the lower limnic unit described in the 60s, and we went much deeper into the layer. So basically, we are at the beginning of the formation, somewhere at the beginning, or at least as much as we could. Okay, this is the trench, this is the location of the core, and the projection here toward the units. We also choose this site because there is a prominent limestone unit, a limnic lacustrine limestone, which can be traced until near the core location and can be identified as well in the core. So it is a very good marker unit in order to connect the core with the exposure in which the major archaeological and anthropogenic work is done. So here you can see the core in front of you, very well laminated, very well layered. This is the top, this will be the base, around 70 meters in long. And as I mentioned, the core appears to have reached deeper layers that are not exposed in the outcrop. The deeper units are characterized by extremely well laminated layers of brown and gray clay units, pointing to the lack of bioturbation, which is not the case for the upper part of the core. Probably calm water conditions and perhaps high lake stands. So we are probably also here facing a high lake stand and a low lake stand toward the top. The new core sequence also appeared to show us some such as cyclicity, and maybe with improving the chronology, maybe we will be able to link it to orbital forcing. In general, the different sedimentary phases that we see is we can see 6 major sedimentary phases. We can see carbonates, is in the upper part, friable homogeneous silt, then brown laminated clay silt, some heterogeneous consolidated sandy silt, laminated gray, and massive gray clayey silt, very well laminated. This is, if I see this core, I will think this is the Dead Sea, but it's not. This is 1.5 million years old Lake Uberia, and a massive clayey silt, more brownish. So all of these different sedimentary phases are pointing to different conditions of the lake, probably pointing to different stages of development, or high lake level, low lake level, more oxic or more anoxic conditions at the bottom. So here is again the picture of the core with the lithology interpretation here with the different colors which are depicted here, and what you see here is also the organic carbon content, inorganic carbon content, and major elements that we have measured with the end member analysis. I estimate that this is a little bit more complex to interpret rather than the Erek El Ahmar, basically because here we probably have what I see here is much more events probably that maybe they are related to seismicity, or maybe they are related to storms, one way or the other, we see a very strong variability in the end members of the grain size, which not only are related to the varying histology, but also to events that probably are hidden and we need to identify them. But in general, what we see here is again 3 units, at least as much as I can identify here. In this core, unit 3 to 1 from bottom to top, and which are also pointing, and these are basically identified by major trends in the different proxies, such as increasing organic material toward the bottom here in unit 2, or increasing carbonate toward the top between 2 and 1, or increasing quartz between 2 and 1, which I will say it is changing between a high lake level condition and low lake level condition. Here marked in blue will be more high level conditions in units 3 to 2 and low level conditions in unit 1. So we have some kind of cycle here, turning from high to low. So next step will be to do the biomarkers as they were done in Erkel Lachman, and we are doing them actually right now. And if we go for another site, which is in southern Israel, in this case, this will be Lake Kuntila, which is this one here. So this is a map published in 2018 by Ginat and co-authors. And you can see here the prevalence of several lake systems during the late Pliocene and early Pleistocene, mostly early Pleistocene. Also here, the chronology can be a little bit complex, but these lakes don't exist anymore. And especially when I'm talking about Lake Kuntila, it occupied an area of 300 kilometers square, pretty big for this part of the planet, in the southern part of the Negev in Israel, and most of it was in Egypt. And the sedimentary records indicate that the hydrological balance during this time was favorable for supporting a perennial and relative deep lake, and this is what I'm going to show you. Now, this area currently over around 10 millimeters of rain only falls in this area, so obviously the same precipitation pattern was not the same during the early Pleistocene, because such a precipitation pattern will not succeed to sustain such a large lake system. So when we have a look more in detail about here, we can see the reconstructed watershed of the area with the fluvial systems draining the area into Lake Kuntila, which was an open lake system, drained to the north toward the Dead Sea. Interestingly, what you can see here is that part of this drainage was faulted by the development of the Dead Sea fault here. So we can see also these fluvial systems, that they are the ancient fluvial systems faulted. But still, we are talking about an open lake system, and for sustaining an open lake system, not a closed one, we need a lot of water here. So I'm showing you here the Kuntila Gate, which is just next to the border with Egypt, and at the end of the lake system toward the riverine system toward the Dead Sea. So this is the conditions, as you can see, extreme desert. There are no trees, nothing, some shrubs. And we went in 2004, it was 4 years ago, with Yoav Avni from the Geological Survey, Stefan Mischke for the Ostrocod from Iceland, and Juan Larrazaña from Spain, from University of Zaragoza in Spain. And we went there for 3 days to redo the outcrop. It's very complex to get there. It's very far. You need 4x4 wheels, and you need only a time frame in which you can get there. Since it's very close to the border, you need authorization, and we got it for 3 days, so we just went there. We did again the columnar section that was initially done by Yoav Avni and published in 2000 and something. And here we measure the grain size, and we also did geochemical measurements. and total inorganic carbon measurements. Based on the data, what we see here is, again, several units. In general, we see also a transition of the lake, what we interpret as transition between relatively high to relatively low. We don't know exactly the depth of the units, but when we are analyze the depth of the lake, sorry, but when we analyze the ostracod fauna, we see that although Lake Contilla constrained with very few species of ostracod, but and most are recrystalline stations of the Euralin cypris torosa, which is very common in this area, but some of them they are of the Iliocypris, which Iliocypris. I'm not so keen in the Latin names, so sorry for that. Which is a typical of freshwater and running water, and the Candoma, which is a freshwater environment. So basically, what's the main point here is that it was a brackish lake changing into freshwater and running water. And this is the outcome. This is the interesting point here, that we need a large amount of rain, a lot of rain, in order to sustain such a lacustrine system. We tried, we did also the chronology with the help of Juan Larrazoana, he's a paleomagnetologist from Spain. So we sampled the sequence for Panama. What we can see very clearly is a change in the middle between a declination and inclination, basically pointing to a normal period in this. The half of the formation is normal, and the upper half is a reverse. Now we don't know which normal and which reverse, which this is what happened with paleomagnetism, right? But what we do know is that the upper part, the upper layer here, which is a terrace, basically, fluvial, more fluvial. The lake was basically ended, and it was prevailing of fluvial material here. There are here remains of stone tools. Okay, this is for illustration purpose only. Okay, but what we can see is archaeological artifacts of the Acheulean culture that were published as with cosmogenic isotope. This unit for 1.9 or 1.6, depending the site, million years ago. So when we do some kind of an extrapolation, somewhere we are just below this unit, and we propose in this paper that was published a couple of years ago, we propose that this is the transition of the Olduvai to the CR1, which is basically pointing to the 1.8 million years ago. This is our interpretation of this site. So basically, we have another important point in the map, in the transect, in the natural bridge that led humans, early hominins, outside of Africa toward Asia, not only the Ubedia and the Amnisi Cave and other sites, but we have another point in the map which humans, early hominins, sorry, they had water for prevalence and sustainability along the way. So pointing to the point of all the amalgamation of this data is basically that we have different conditions occurring during the Pliocene and Pleistocene. When we have a look on the Levantine corridor, which is the only land bridge connecting Africa with Asia, the area is currently influenced by the westerlies, as I mentioned, with winter rain, which is the one that is happening outside my window today. But my point is that even if the westerlies were providing with rain and precipitation during the late Pleistocene, as is very well identified in the Dead Sea, we are still not so far from the ITCZ boundary of summer monsoon rains. And my point is that we probably have been influenced with northward migration of the monsoonal rain system since the Miocene. and with tropical storms emerging from the Red Sea trough related to the northward migration of the monsoons. It will be impossible to put the monsoon in the Levantine region, and I'm not aiming to do that. But it is possible to provide water to the region with tropical storms coming from the Red Sea trough related to the monsoonal system during the transitional periods, and that they were more active during the Pliocene. So basically, we are not so far from the global monsoon systems and probably influenced by it during the Pliocene. So as a summary and conclusion, we see in the marine a well-channelized sequence that was identifying the Pliocene succession of the Levant basin with channels, with two types of channels, V-shape, U-shape, their geomorphology pointing to a sea level of oscillation, but not only, also for monsoon-related precipitation in East Africa, which is an extratropical fingerprint of that. Then we have lacustre formations pointing to three different lakes, Erek El Ahmar during the Pliocene, and two of the lakes during the Pleistocene, the Kuntilla and Ubedia. And these were large lakes which are not sustainable in the current conditions, and some of them were pretty deep lakes that are identified by the anoxic conditions in some of the bottom of this lake, at least in Ubedia or Erek El Ahmar. And all of them appear to have been with freshwater conditions, sometimes brackish, but mostly fresh. We see in Erek El Ahmar carbonates, we see in Kuntilla, which is in the southern part of Israel, we see freshwater ostracods, and in Ubedia, we're still developing the project, but we definitely see freshwater taxa, fauna. And pointing to totally different conditions and that are not the one that we see today. So both marine and acoustic records point to an increase in moisture in the region and possibly influence tropical sources of humidity, perhaps related to the monsoon during the Pliocene, and that they were diminishing toward the Pleistocene, but we still see the effect with that. And obviously, all of that have major influence of our evolution, since the area has been the locus of human migration in our ancestral history, not only out of Africa, but also coming back into Africa. We need to remember that there was no sign point for migration. We were going north and south along the region. So it's very much important to understand what were the environmental conditions in this part of the planet in order to understand our own adaptability to these conditions, how we humans adapted along our evolution. So obviously this is not me and myself here. I have a bunch of people behind this project, and some of them already left the lab. John Kingsley is currently doing his PhD in Erek El Ahmar. John really finished his master degree also in Erek El Ahmar. He's currently in Syracuse. Chrissy Hall was a postdoc alongside as Dean, also working on Erek El Ahmar idea, and Ankit is currently in Germany working with in the group with the biomarkers. And of course, Nimerta, the lab manager. Without him, anything can be possible. So I would like to thank them, of course, and thank you for listening. And I'm open for questions, if there are.
Thank you so much for your talk. Who doesn't love a good lake sequence, especially several of them, in such an important and interesting area. So we'll let people think for a moment here and type questions into the chat, and then I can call on them for question, or alternatively, you can kind of raise your digital hand and I can also call on you. So while people are coming up with the questions, I do have a question.
Yeah.
So you mentioned that you think that maybe some of these sources of moisture are coming from tropical areas. So I wondered if maybe there were, let's say, supportive or corroborative evidence from speleothems that might have been recovered over the same time periods as some of these lake systems that could maybe like pinpoint like, oh yeah, we think that's happening, but let's, find the smoking gun in the lake sediments.
Yeah, absolutely. Your question is very timely. I didn't show that, but considering the Pliocene, if we go to the Pliocene, it's a little bit complex because dating of speleothems is kind of tricky, as you know, for the Pliocene, but there are evidence of older than Pleistocene speleothems in the region, in the Negev Desert and in Saudi Arabia. These are works of Dominic Fleitman from Switzerland. But again, Pliocene speleothems, it's tricky. Talking with a colleague of mine from the Geological Survey, Anton Vax is the one that published here about early Pleistocene speleothems in the Negev Desert in southern Israel. So he sees them, he published them. But verbally, he told me he found caves with speleothems. He thinks that they are Pliocene. He is trying to prove that. But what you see is very large crystals pointing to a lot of water. This is what verbally, and he showed me the crystals. So you see large crystal, you see something which is older than, but still the age is problematic. So I cannot really tell you, okay, yeah, we have also the Pliocene caves because we don't know if it's a Pliocene, but we do see early Pleistocene caves for sure.
Oh, excellent. It seems like you're coming to kind of this critical mass of information to kind of start putting all of this hard work that you and your colleagues have done. So that's really cool, actually. Nice.
Yeah, no problem.
I see we have a hand up in the audience from Paul Wilson. Would you like to ask your question, Paul?
Thanks a lot. I enjoyed the presentation. Thank you. And maybe the question is kind of following up on the previous one, really. You allude to a monsoon source for the water, whilst recognizing that, well, today the main rainfall that occurs at these latitudes is sort of a winter phenomenon on the westerlies. And so it would be, I guess, two things. It would be good to kind of hear a little, maybe give you a chance to expand a little bit more on why you perhaps emphasize a monsoon mechanism over a winter mechanism for increased rainfall, and secondly, I would really love to hear a little bit more about the precise mechanism that you invoked, the tropical storms via the Red Sea Trough.
Okay, so there are two questions. Yeah, first of all, well, I don't have the slides prepared for explaining you about the tropical storms related to the Red Sea Trough here. But basically the area, let's start by the present. The area in the Levant is, most of the rain comes during winter, of course. It's a Mediterranean type of climate, influenced by the westerlies, and providing the precipitation due to the Cyprus low, okay, which is dominating above Cyprus, Turkey, and over there, and providing with the rain during winter. But during the transitional periods, which is basically traditional seasons, I may say spring and autumn, we do have influence of the tropics with the Red Sea Trough, which is a very high wind coming from the Red Sea, very high, providing with humidity from actually the east and southeast during those periods. This is what is the current situation. Now, obviously, these winds that actually provide also with rain, they are not sufficiently enough for sustaining a large lake systems, but they do provide with water to the system, to the area. And we did experience this year a very strong storm, actually, at the beginning of the winter, because here, basically, in Israel, we don't have a spring and autumn. Is boom, we change from one season to the other, and we call it spring, but it's not really a spring. I mean, it's boom, that's it. I mean, it's very quick here. But we did experience in the autumn a very strong storm of a lot of rain coming actually with the Red Sea trough. It was a couple of months ago, and it was very substantial. I mean, some of the cities were inundated actually. So when we go back to the data. But I also see in the basically what I don't show here is the Dead Sea, because this is the middle Pleistocene, and I concentrate the talk in the early Pleistocene and Pliocene. But I did work in the middle Pleistocene Dead Sea, and in the middle Pleistocene Dead Sea we are dealing with the formation, the Amora formation, which basically cover a time span which is 800,000. Let's make it round, 800,000 to 130,000, which is a long time span of record, continuous, totally continuous, more than 400 meters of a formation which is all exposed and tilted because of the diapir, which is rising south of the Dead Sea. And we see units of high lake level, low lake level, high lake level, low lake level along all this huge time span, and analyzing the geochemistry there in comparison with the chronology, comparison with other data which comes from travertines, we see that there is actually low lake levels, okay, with travertines in the Negev desert. And travertines, the only way to form it is with a lot of water coming from springs, okay, and a lot of water that maintain the springs. So the interpretation, that was a paper published in geology in 2010. So the interpretation was that we need a different system to pump the water into the springs in the southern part of Israel, and it's not the westerlies. Otherwise, the westerlies will maintain the lake level high. The westerlies is the one that maintains the lake level high all the time. All the time we have a lot of rain, we have flash floods, and the lake level is kept. At least I'm talking in the millennial scale. But when we are talking about a low lake level, you have a lot of travertine in the Negev desert, or otherwise speleothems also in the Negev. Okay, following Tara's question, you have a different system. That water doesn't come from the westerly. Otherwise, you will have also a high lake level. Okay, so that in order to pump the system with water in the southern part or in Saudi Arabia, which also exists, so you need a different system, and it's not the westerly. It's something from the south. Now, that's the point of having a different system. Otherwise, you will be in a high lake level, especially in the rift, in the Dead Sea, which is the Dead Sea itself, Lake Ubedia in the past, or other systems, or Lake El Ahmar or other lake systems that were existed. All the time, they provide, the water comes from the westerly. But I wonder, the Pliocene, maybe the water, the more water came from the Pliocene. I mean, it was not as few as now, and maybe we had more events coming from the south, more events coming from the Red Sea trough in relation to the monsoons. It will be impossible to put a monsoon at this latitude. It would be wrong for me to say monsoons reach this latitude. Every climatologist will cut my hair, okay? But we don't know the Pliocene. The Pliocene, there are influence of the Red Sea trough related to this. So this is what I'm pointing to. Okay.
Yeah, thanks for that. That's an interesting and helpful answer. Although I would, I would add that some climate models do make your part of the world unrealistically wet, even when they in a modern simulation. From the south. So yeah, but thanks. That's really helpful. Thank you.
No problem. Thank you.
Do we have any more questions from the audience? Give everybody a moment to pump prime their question. Much like the springs of the last question. No? Okay, well, let's put our physical hands and digital hands together for our speaker for today. Thank you very much
Thank you
for
very
this
much.
talk.
Thank you. Thank you, everybody. And yeah.
I look forward to seeing more come out of your lab. It seems like, again, you've got this critical mass of data that's just about to start breaching a little bit of what you're talking about. So yeah, thank you very much. So before everybody runs away, I just want to remind everybody we do have a Monsoon seminar next week, but on the alternative schedule. So instead of being on schedule B, that is friendly to this, basically, I would say Asian time zones more or less and European time zones, it will be on schedule A, which is kind of more of a North American and South American time zone favoring. So I hope everyone has a great rest of your morning, afternoon, or evening, wherever you are. And I'll see you again next week. And so thank you so much again, Nicolas, for your lovely talk.
Thank you. See you.
Bye, everybody.
Bye.